All right, we're going to continue on with Unit 4, second part of chemical reactions. Today we're talking about just the redox reaction part of it. We're going to have a couple examples of an oxidation reduction reaction in an acid and in a base. Um, it takes a lot of room. It's a lot of work. It's one of the harder examples of an AP Chem problem. So we're going to tackle that today. I hope you're excited. All right. So a redox reaction is a reaction in which electrons are transferred from one compound or one atom to another. Electrons are being moved around in this chemical reaction. Um, this happens in a lot of different types of reactions, and we're going to learn how to be able to identify it today. We need to learn more about oxidation states. Oxidation states are basically the charge an atom needs to satisfy the octet rule, or to be stable, however you want to think about it. But we're going to use it today as a way to keep track of our electrons in an oxidation reduction reaction, especially with covalent substances, which we'll talk about. Oxidation states of atoms in covalent compounds are obtained by arbitrarily assigning electrons to particular atoms. Okay, so we need to be able to assign oxidation numbers to compounds, a bunch of different types of compounds. There's like 6 different groups if you look at your notes that we're going to go over. There are kind of some rules that we're going to use to answer the questions at the end. Questions at the end is I'm going to give you a compound. You're going to tell me the oxidation number of each individual atom in that compound. Sometimes it's very obvious. Sometimes you have to do a lot of work to kind of puzzle it out. Rule number 1. Each atom in a pure element has an oxidation number of 0. If it is not bonded to a second type of atom, it has an oxidation number of 0. It is pure. All of these examples, I2, copper, a diatomic gas, a metal just by itself, oxygen, P4, S8, doesn't matter how big the numbers get, if you have just one type of atom, it has a 0 oxidation state. Okay. If you have an individual ion, though, it's going to have the number equal to its charge. So like Mg2 plus, if I have that by itself in a reaction, its oxidation number is just its charge, 2 plus. H1 plus will be 1 plus. Now we're going to get into the more complicated rules. Number 3, group 1 elements have an oxidation number of 1 plus. Group 2 elements have a 2 plus. Group 13 have 3 plus. So these are consistent. These are the ones on our periodic table we've already labeled. Everything in the first column usually has an oxidation state of 1 plus. Second column is 2 plus. 13th column over here is 3 plus. Those are what we have written on our periodic tables. Those are what we've always used. So here I have NaCl. I know the Na is 1 plus. Ca, the Ca is 2 plus because it's in the second column. Lithium's back in the first column, so it's 1 plus. Those 3 are going to stay how we've learned them so far. But you'll notice, or you'll learn, some of the ones on the right of that, anything in 14 through 17, they actually can change. And that's one of the things that make this tricky. Fluorine is a friendly example. It always is 1 minus. So fluorine is always 1 minus when it's bonded to other things. Nothing's going to override that fact. So HF, the F must be 1 minus. BF3, the F must be 1 minus. Okay, H and O are the next ones we're going to talk about. The H is almost always 1 plus. There's an exception we're going to talk about below. Exception 1. When H forms a compound with a metal, it'll have an oxidation number of 1 minus. H can either get to 0 electrons or to 2 electrons to satisfy its octet rule, so it can do either. This example here at the bottom, LiH, this is very rare. This isn't usually going to happen. H is almost always written first in a chemical compound, like H2O, HCl. In that case, it's going to be a +1. This is the only example here that it's going to be a -1, because it can also act as a non-metal sometimes. H usually is a metal, though. So H will almost always be 1 plus, but do be aware in a situation like this, where lithium has to be 1 plus because it's in the first column, H can be 1 minus sometimes. Oxygen is almost always 2 minus. In every compound, it's 2 minus except for 1. When it's in a peroxide, hydrogen peroxide is H2O2. That is the one time when oxygen doesn't have to be 2 minus, it is instead 1 minus. Okay? A lot of rules and exceptions to kind of learn that we'll kind of practice in the next part, but like I know it's a lot to remember. And then the last thing here is the sum of oxidation numbers in an entire compound is always 0 if it's neutral. And if it's a polyatomic ion, it must be equal to its charge. So if you have a full compound with no charge at the end, like a normal compound, the sum of all those oxidation numbers must equal 0. And if it's a polyatomic ion, it must equal the charge of that ion. In this example here, I have hypochlorite, right? Has a charge of 1 minus. So if I add up all the oxidation numbers inside of it, they must equal 1 minus. Oxygen is always 2 minus. So therefore, I'm able to kind of reason out what chlorine must be. Chlorine must be 1 plus to make it equal 1 minus. So this is kind of like a math puzzle. Some people love this, some people hate this. But let's do some examples. Pause for 1 moment while I remove these spoilers. Well, whatever. Okay. So the first one there was CO2. We want to think about the oxidation numbers of C and O. Oxygen is one of our rules. It's always 2 minus unless it's in a peroxide. This is not H2O2, so oxygen is going to be 2 minus. Okay. Now there's 2 oxygens here. Each oxygen is going to be 2 minus, so that makes a total of 4 minus. Now I need to figure out what carbon is. This whole compound has a charge of 0, which means the oxidation states must add up to 0. To make 4 minus cancel out, carbon must be 4 plus. 4 plus minus 2 equals 0. So if I sum all those oxidation states, it equals 0. That's how I can figure out what carbon is. Let's try a polyatomic ion. I have dichromate, Cr2O7, 2 minus. I'm going to start the same place. Oxygen's always 2 minus. I have 7 of them this time, so that makes a total of 14 minus. This time I have a polyatomic ion. Its charge is 2 minus overall, which means I need to make this entire compound's oxidation state 2 minus. Okay. So basically I'm writing an equation. Okay. I have 14 minus equals 2 minus. It might help if I write it like you actually write math. Negative 14 equals negative 2. All right, well, I need to add this negative 14. I have 2 chromiums. So what number does chromium need to be to balance this equation? Okay, well, I have 2 of them. They need to equal 12, if I add 14 over here. To balance this out, divide by 2. Each chromium has to be 6. So if this chromium is 6 plus, and there's 2 of them, that's 12 plus total. This is 14 minus. Add those together, it equals minus 2. Everything cancels out. So it's kind of like solving a math puzzle. Next, H2SO4. Need to figure this out. H is always plus. 1 plus. Oxygen's always 2 minus. I need to figure out what sulfur is. It needs to equal 0 because there's no charge here. So this is minus 8. 2 times 4. This is 2. To make this equal out, sulfur must be 6 plus. So if I add up 1 plus plus 1 plus plus 6 plus minus 8, it equals 0. NO2 plus. When I finish, this needs to equal 1 plus. Oxygen is always 2 minus. Times 2, this equals 4 minus. To make it equal plus, this needs to be 5 plus. It's 5 plus 4 minus equals 1 plus. Determining oxidation numbers is a really important part going forward for what we're doing. We're going to have a lot of practice of this in class. I'm just going to give you a list of these types of compounds and all the different polyatomic ions and make you figure out all the oxidation numbers of everything. Now we're going to talk about redox reactions. Redox characteristics. A redox, like we said, is a transfer of electrons. Transfers may occur to form ions, and we're going to look at two different terms here. Redox is made from two different words, oxidation. Oxidation is a word you might hear like when you talk about things rusting. It's like something's oxidizing. Well, it's an increase in its oxidation state, meaning a loss of electrons. When something oxidizes, that means it's losing electrons. Reduction is the opposite of that. It's a decrease in oxidation state or a gain of electrons. Okay. The way to keep that straight is with this saying at the bottom. Leo the lion says grr. Leo says grr because it's a lion. Right? Lose electrons oxidation is Leo. Gain electrons reduction is grr. Okay? So keep that straight. Leo says grr. Lose electrons oxidation, gain electrons reduction. You need to identify sometimes in a problem which things oxidize, meaning they lose electrons, which things reduce. Okay. Which of the following are oxidation reduction reactions? Okay. Let me go back for a second. Okay. I have three different reactions here. I need to determine which of these are a transfer of electrons. What that means is the oxidation number of something in the reaction is going to change from the reactants and products. So let me copy these down. Okay, so A said Zn. I'm going to ignore the states that matter just to save time. 2 HCl's makes ZnCl2 and H2. So I need to identify in this reaction, does anything's oxidation number change from the left and right? If even one thing changes, it is a redox reaction. I'm going to start with zinc. Over here, it is pure. It is by itself, so it is 0. Right? Anything by itself is 0. Over here, zinc is with chlorine. Chlorine this is an ionic compound. In an ionic compound, you just use their normal oxidation states. So chlorine is 1 minus. There's 2 of them. Zinc is 2 plus. Zinc goes from 0 to 2 plus. That means this is a redox reaction. It is changing its oxidation state. Let's try to think, is this losing electrons though? Or gaining electrons? Its charge is going from 0 to positive. Okay. If you're gaining electrons, you'll get more negative. If you lose electrons, you get more positive. So losing electrons, oxidation. So in this reaction, zinc is being oxidized. Okay. So this one is one of the correct answers. A is one of them, but let's check the other ones too. Second one here, I have my chromate again, plus 2 hydroxides, makes you 2 chromates plus water. So if I can find at least one thing that changes oxidation state, it is a redox reaction. So let's break it down. Chromate, we already did this example. The O7, that's 2 minus, equals a total of 14 minus, but I need the total to be 2 minus, so this needs to equal 12. There's 2 of them, so divide by 2, 6 plus. Let's see if the chromates and oxygens over here are the same. This chromate is 2 minus. Oxygen must be 2 minus here. Okay. 4 of them, so it needs to equal, this is 8 minus. But the total is 2 minus, so this needs to be 6 plus. All those are the same so far. Let's check the other O's. This one here is 2 minus. So this hydrogen, to make it equal, must be 1 plus to make it equal minus overall. Over here, same thing, 2 minus, 1 plus. This equals 0 because there's 2 pluses, and like that. All of these numbers stay the same on either side. All the O's are -2 throughout. All the chromiums are 6 pluses. Hydrogens are all 1 plus. This is not redox. And then the last one real quick. Okay, I have some copper chloride making other copper chloride and copper. Well, this is 0 because it's by itself. This copper here had to have been a 1 plus charge, and this one was a 1 minus charge. Know that because this is an ionic compound, so the oxidation states come from the numbers. There's 1 of each of these, so I knew there's 1 plus charge for each one. This one was made of copper 2 plus and Cl 1 minus. So this one is a redox. This is probably confusing looking. It's supposed to be an arrow. Because copper changes. So A and C are both redox reactions or oxidation reduction reactions. All right, we're near the end here. Another super long set of instructions. These problems are pretty intense. I left you an entire page for each of them. This is a special method for balancing redox reactions. Here are all the instructions. I'm going to show you how I do it. I follow those instructions, but it just doesn't make sense to write like that to me. Balance the following reaction in acidic solution. Okay. First, acidic solution. What that means is we're going to be in an acid. In an acid, you have things floating around. Specifically, you have H pluses. It's kind of the definition of an acid is you have these H pluses floating around. You also have water floating around. So an acid is basically just by definition something that contains water and H plus ions. So we'll be able to add those to our reactants and products as we need. I'm going to go ahead and write my equation. Our goal is to balance this equation. But we need to balance not only just my number of ions or my number of atoms on each side. I also need to balance the charges, so the charges equal out. Like this Fe2 plus and Fe3 plus. I need to do something about that so it balances out. I want to do what we call the half reaction method. I want to split this into 2 different half reactions. So I'm going to take this MnO4 minus. It turns into Mn2 plus. Because those 2 things pair together well because they both have Mn. Then I'm going to take these other 2, Fe2 plus yields Fe3 plus, and pair those together. I'm going to split my one reaction into 2 half reactions and tackle each one separately. Starting here, the right one's easier. Let's start there. I have 1 Fe on each side already, so they're good, but my charges are not balanced. So I have an extra positive charge over here. So what I'm going to do is I'm going to add 1 electron over here. If I add 1 electron, that negative charge balances out, and now both sides are equal. It's just supposed to be there. Normally you don't add in electrons like that, and they're not going to be in our final answer. They're just kind of an intermediate we're going to use to help ourselves balance them. So we're just going to leave that for now. The right side's good. Left side, let's balance. First, my MNs, I have the same number on each side, so that's good. But I have these O4s, and I have no oxygens over here. So I need to add oxygen to the side to balance out these oxygen. That's where this acidic solution is going to come into play. I can add some H2O to this side until I have the right number of O's. If I add 4 H2O's over here, 4 O's, 4 O's. So that's good. My oxygens are now balanced. That's going to be the first thing you do. Make sure, well, first you make sure manganese is balanced, and then you're going to go to everything else. Oxygen. It's now balanced. But I added these extra H's. Well, I can add some H pluses to counteract that over here. I have 8 H's over here, so I'm going to add 8 H pluses over here. Now all my atoms are balanced. All I can do is add coefficients in front of things and add in these 2 compounds to balance them. But the only thing that's not balanced here is the charges. This is a total of 8 plus and 1 minus. So this side has a total charge of 7 plus. This side is only 2 plus as its total charge. So I need to balance that out by adding some electrons. So I'm going to add 5 electrons over here so that my charge on each side is now 2 plus and balanced. Okay, so now I've balanced each side of these separately. The charges and the atoms are balanced. I need to add them back together. But my goal when I add them back together is that the electrons cancel each other out because they cannot be in my final answer. I can't just say I have electrons coming out of nowhere. So I'm going to times this side by 5, everything, so I have 5 electrons to cancel with these 5 electrons. Okay, so I multiplied everything by 5, so it cancels out when I add these back together. So I'm going to attempt to add these two things together. I'm going to take this reaction plus my new reaction over here. I'm going to add together any like terms. I can cancel out anything that's on both sides. But I'm just going to add everything that's on the left of the arrow together, everything that's on the right of the arrow together over here. But importantly, I have 5 electrons on each side, so those cancel. So over here, I'm going to add my 8 H pluses plus MnO4 minus plus 5 Fe2 pluses. All those 3 terms, add them all together. Do the same on the right. Okay. That is my final answer here. If I check, every atom is balanced. I have the same number of manganese, hydrogen, oxygen, and iron on each side. Okay. Also, my total charges is balanced too. I can work it out. This is 8 plus, 1 minus. This is 10 plus. So there's 17 plus total charge on this side. So on this side, it must also equal that. 2 plus, 15 plus equals 17 plus. This is a fully balanced redox reaction. The reason we have to do all this weird method is because you could just try trial and error with this until you get it fully balanced, but it's like impossible to guess at. So this is a method to balance a redox reaction. That would be your final answer. Remember, this was in acidic solution. Acidic solution means you should have some H pluses floating around and H2Os floating around, which we do. Next problem actually is going to have a few more steps after that. Let's move on to that last problem. All right, here is the method for the basic solution. Everything's the same except for what's in yellow. So if you want to write that down, when you get to your end, a basic solution is only going to have 2 other things floating around. They're going to have H2O, but in a base, there's not H plus floating around. There's hydroxide. OH minus is our free ion floating around, making it basic. So we're going to have to do something else at the end, which I'll show you. Okay, so pause the video there, watch, copy that down, and then do this last example. All right, so here is my new reaction. It's in basic solution, so we'll have to take that into account. I have H2Os floating around, and OH minus is floating around. I'm going to write down my equation. Now I need to balance it. Split it into half reactions. The HS and the S will go together. The chlorate and the chlorine will go together. Balance each one separately. Keep doing this today. What the heck? All right. S's are good. I have 1 S on each side. So let's move to H's. Well, I need to add an H plus to balance that out. Now I know I just said we have OH minuses floating around. But to do this, we're actually not going to start with that. We're going to do this step later. We're going to treat this just like an acidic one until we get there. So I'm going to add an H plus. Adding an OH minus, you can do that here. It's just going to really complicate it. Because then you have to add in H2Os, and it's really going to mess up your reaction. Okay. So we're just going to add in an H plus, so I have an H on each side. Now we need to balance out the charge. This side is 1 minus, this side is 1 plus. So if I add 2 electrons over here, everything is good now. 1H, 1S, and a 1 minus charge on each side. Over here now, we need to balance our chlorate and our chlorine. I have to add some H2Os. I have to add 3 of them. So I have 3 O's over here and 3 O's over here. But now I need to balance out my hydrogens. I have 6. So I add 6 hydrogens over here. Now I need to balance out my charges. This is 6 plus and 1 minus. This equals 5 plus. This is just 1 minus. So I need to add 6 electrons to make them equal. That half reaction is now balanced. Okay. Now I need to combine them back together. Before I do, I need to make sure my electrons cancel out. So I got to times everything here by 3, so it equals 6. So I'm going to have 3 HS 1 minuses, 3S plus 3 hydrogens plus 6 electrons. All right, let's go ahead, add my 2 reactions together. You don't have to rewrite everything out like this, but I think it helps. Add those 2 back together. 6 electrons cancel. Okay. I can cancel some other things to help as well. On the right side here, I have 3 H pluses. I have 6 over here. So I'm just going to simplify it, make that 3 instead. Nothing else matches, so I'm just going to add those 2 together like that. Okay. That is my balanced reaction, if it wasn't acidic. This is your final answer for an acidic solution. But this is basic. A basic solution doesn't have H pluses floating around. It has OH minuses floating around. What you need to do once you do a basic one is get to this step. We're going to neutralize all of these H pluses. I have 3 H pluses. I'm going to add 3 OH minuses to neutralize it. But whatever I add to that side, I must also add to this side. So I'm going to add 3 OH minuses to both sides. These are going to neutralize and actually make water. H plus OH minus makes water, and it makes 3 of them. Common mistake is to write 6, but remember, you only have partial ingredients here. You have 3 H pluses, 3 OH minuses, so you have a total of 3 H2Os. Okay, added everything together, added an OH to both sides. Next thing I notice, I have 3 H2Os on both sides. Get that out of there. Simplifying your reaction is always best. And I get to this is my final answer. This is my fully simplified reaction, completely balanced. I have the same number of each atom on both sides. My total charges on both sides are equal. And it's balanced in basic solution, because now I have some free-floating OH in a basic solution, which makes sense. I don't have any H pluses. That whole thing is basically it. That's how you do a redox reaction balanced in basic. We're going to practice this a bunch. These are some of the harder problems that we do. I know it seems like things come out of nowhere. It's totally fine. We're going to practice this in class. Make sure you watch this video. Make sure you watch the previous video as well, so you can have all of Unit 4 notes done for when we return to school. Okay? All right. Enjoy the rest of your break. See you guys soon.